Hi, it's been a while since I've done an update on the RIBBIT65, so I thought I'd give it a shot. So I've put together a little presentation to kind of walk us through what's been going on, and then after that I'll do some demos with the actual RIBBIT65, and that's basically the plan at this point. We'll go through some of the steps going forward. So let's get started. So, the state of the RIBBIT65 in November 2021. What is going on? So, I have done a redo of the RIBBIT65 Core board, and it is now the RIBBIT65 Core Plus. You'll notice that the address decoding is now 4 chips instead of 2. These are, Jelly Bean TTL parts, 74 HC series chips. And basically the idea there is to be able to clock gate the address decoding irrespective of whether it's coming from an external source or from the internal source. The effective onboard address decoding is the same as the original Ben Eater address decoding, but the jumpers all the way to the left below the clock oscillator basically allow for an external set of chip selects to be run in, and those are also clock gated. So basically the idea is the system I/O board has more sophisticated address decoding on it to make use of the RAM above the 2 pages of I/O at address 6000 hex, and it also breaks out the first 8K of ROM from the rest of ROM, so that the pageable ROM functionality can be utilized. So there are 3 inputs. One is for RAM, one is for core ROM, and one is for pageable ROM. And that's what those jumpers are for. There's some other jumpers on there for power and clock and some of the control signals like IRQ and NMI and BE and stuff like that, where you can inject signals. And yes, you can do that on the bus as well, but just having the ability to use pull-up resistors or not seemed like a good idea. So I went ahead and built that into the board. And at the bottom right, you'll see 2 10-segment LED bar graphs with unpopulated chip sockets, and that turned out to be an error. I used the wrong chips to drive those LEDs, and so the version of the board you're going to see later has that unpopulated. I've done a fix of the design. There's also a bodge here, but I've done a fix of the design where the blinking lights will work. So if you decide you want that, if you're building one of these, you can just populate it with the parts and it should work. So the big chips in the middle there, all the way to the right, is the CPU, and the eagle-eyed among you will notice that the notch is pointing toward the top of the board, which is different from the original RIBBIT65 core. I ended up having to do a bunch of vias to accommodate the orientation of the chip, but that's life. So moving left of the CPU, there's the ZIF socket for the ROM, and then left of that is the RAM. To the left and slightly above the RAM is a power on reset chip. That's a DS, I believe it's a DS1232. And some of the people that I mentioned this to suggested a simpler Dallas reset circuit, and basically a TO92 case with 3 pins on it. And while that's cool and everything, I wanted to condition my reset pulse from a push button switch through the same chip, so that I didn't have to try to make sure that the reset pulse coming out of the push button switch was also clean and not bouncy and all that kind of thing. I mean, it's not super critical, but the DS1232 was more of something. It was a more versatile chip, and it's something that I wanted to have in my parts bin anyway, so I just went ahead and went with it. It's a little more expensive, but no big deal. So yeah, that's pretty much the RIBBIT65 Core Plus. There are 2 bus connectors on the right side. The one furthest to the right is intended to be just the regular bus connector, so you can hook it up to whatever. The bus connector on the left is intended as a diagnostic / auxiliary bus connector. For example, if you've got to connect to bus signals with an O-scope, it's going to be a lot easier poking a jumper wire into one of those sockets than it is trying to hook a mini grabber onto an IC leg or something like that. So that was just a kind of an accommodation of one of the troubleshooting difficulties that I'd run into on the RIBBIT65, the original RIBBIT65 core. So on the Core Plus, I validated that the power on reset works. It required 2 mods. One is a bodge wire that runs from the reset NOT on the DS1232 to pin 40 on the 6502. And that was down to an error that I made in designing the part for the DS1232 in KiCad. That has since been resolved, and the Rev 0.2 version of the Core Plus board has that fixed. There was also a need for a pull-up resistor on the reset NOT that I neglected to put in, so that is also in the R0.2 board. The RAM and ROM chip select injection with clock gating works. Address decode, like the Ben Eater type address decode, which I've reworked a little bit, but in terms of the individual gates and all that kind of stuff, but that works. Selectable pull-ups for the CPU control lines, that all works. The thing that is broken, irretrievably broken in this version of the board is the blinking lights. So that's sad, but I'm finding a way to go on. I've also assembled a cost-reduced version without the blinking lights, without the voltage regulator. Oh, that's something that I didn't mention. We can go back, I guess. So in the upper left-hand corner is kind of the power clock reset section, and the eagle-eyed among you will notice that there are 2 barrel jacks up there. The one at the far left accepts a, you can say 7.5 to 12, 14 volt input. And there's a 7805 on there that should regulate that down to 5 volts. And then to the right of that barrel jack, there is another barrel jack, and that is for unregulated 5 volts in. That is to say, the assumption is whatever's putting power into that barrel jack is going to regulate it to 5 volts. And there's the board, the RIBBIT65 Core Plus board has no responsibility to regulate it. That is essentially the way it was on the original RIBBIT65 Core, but I wanted to be able to accommodate, if needed, higher voltage input and regulate it down. So that's what that is. And user selectable jumpers for signaling options. So yeah, I did a bunch of jumpers in there to just have the CPU control signals that were otherwise not used on the Ben Eater design, to be able to inject signals there as needed to try out different things without cutting traces or doing any kind of nonsense like that. And then there's the RIBBIT65 System I/O board. Since this picture was taken a couple of weeks ago, I have populated the last 2 6551 and Max 232 chips for the third and fourth RS-232 ports, general purpose RS-232 ports. But we're still, as far as what's manufactured, we're still at Rev 0.1, which is the version of the board you see here. And all 5 of the RS-232 ports require the same bodge to reverse the TX and RX data lines between the Max 232 and the actual jack, the DB9 connector on the back. So I have validated address decode and the ROM and RAM chip select outputs. Now that I've got the Core Plus board, I was able to do that. The RS-232 ports all work. The mods were required to reverse the TX and RX data pins, as I said. That has been fixed in Rev 0.2, which is completed in KiCad. I can't rule out the possibility that it might occur to me to try doing something else. But at least these errors were fixed. And the VIA for the character LCD works. This says not yet validated, 2 times general purpose vias. Actually, I have done a validation of write on both ports and on one of the vias, and that appears to be working correctly. So I do intend to basically write a shotgun test program to exercise all of the I/O on the system I/O board that currently exists. So the system I/O board right now does not have any of the I2C or SPI, the storage, all that kind of stuff. That doesn't exist yet. But the 4 general purpose RS-232 ports and the 2 general purpose vias, I want to write an exercise program to basically hit each and every one of them and try to do, at the very least, writes, but possibly reads and writes. And as I said, I've done a write verify on the first general purpose via, both ports, and that appears to work correctly. What I want to do, and I still have some stuff that I need to build out and validate for the system I/O board, but I've been thinking about this for a while, and I definitely want to do it. I want to do a mini ITX version of the RIBBBIT65. I'm fairly confident that in the mini ITX form factor, it's going to be difficult, if not impossible, to get everything on that board. Get the entire system I/O feature set on that board. So I'm trying to make some decisions about what to include into the single mini ITX board, and maybe doing some kind of a mezzanine board. None of this has really been worked out at this point, so I'm not sure what I'm going to do. Mini ITX has a finite volume above the board that it can accommodate, and so I'm going to have to make some choices. We'll see. But one thing that had occurred to me was the possibility of doing like 2 of the serial ports and 1 of the general purpose vias, and like the character display via on with the CPU, ROM, RAM, address decoding, and all that kind of stuff, and the interrupt controller on the main board. So that gets you a console, gets you 2 general purpose serial ports, and 1 of the vias and the character display, all that on that board. So if that's all you get, you still have a fairly functional computer that can do, a worthwhile variety of things. And then a mezzanine board that has the rest of the excitement for the system I/O board. And for those things that would be using the ATX back panel, the I/O panel on the back, those would be connected down through the connectors for the mezzanine board. The ports would exist on the baseboard, on the motherboard, so to speak, and you would just run the signals down through the board-to-board connector and over to those ports. So how much of the system I/O would be available in a mini ITX form factor? I'm not sure yet. I'm considering using new address decoding using an Eeprom rather than discrete TTL chips. I have validated this with a 1 megahertz clock. It seems to work fine. I've gotten some feedback from folks on the 6502 CPU family page on Facebook saying that at higher clock speeds that will probably fall apart, and I believe it. At some point, I plan to try to do some validation of that to see where that breaks down. Because if it's at like 4 megahertz or beyond 4 megahertz, if 4 megahertz is stable, I'm not going to worry too much about it. Anyway, that's kind of that thing, and that Eeprom address decoding will open up some new opportunities for people who are trying to use the RIBBIT65 to do something else. Because primarily, one of the things that I wanted to achieve with the RIBBIT65 was to make it a kind of a lab machine, kind of a Swiss Army knife, Leatherman type of tool that not only facilitated doing interesting / worthwhile / valuable stuff in a lab setting, but also for educational purposes. You know, basically setting up a core basic system that somebody who wanted to learn how to write 6502 machine language or interact with these peripherals or whatever could actually have a good starting point and build on it and try doing neat stuff. So having the combinatorial logic of the address decoding in an Eeprom puts you in a much better position if you decide at some point, yeah, this address decoding is interesting and everything, but I really want to use this additional page up here to do funny third thing. I'd like to take that, I don't know, I'd like to be able to use that 8K pageable ROM space and use it as RAM. Use it as a RAM disk or some kind of crazy thing. Well, you know, you could quite possibly do. So that Eeprom address decoding thing is probably coming in the mini ITX version. ATX power and I/O connections. So the front panel I/O, meaning the power and reset switches and the at least the power light, possibly the activity light, having connections on the mini ITX board, as well as the back panel. At this point, I'm not expecting to do anything that would line up with the one expansion slot that you get with mini ITX. We'll see. What I may end up doing is having a board that exposes a connector that would allow you to do the user I/O board, if there ever, ends up being one, doing a user I/O board hanging off of in a sidecar box that would plug into a connector in that slot. I've also considered doing something where you could put a cartridge slot and maybe an SD card slot or something like that in a 3.5-inch bay, like an exposed 3.5-inch or 5.25-inch bay on the front of a mini ITX box, so that you can, plug in an SD card, plug in a cartridge, all that kind of stuff. We'll see. All this is up in the air, and I'm not making any promises at this point other than basic functionality on a mini TIX motherboard. I have taken a turn with the core ROM. I'm basically doing this thing I'm calling Brave New World, which has startup code. It does not go straight into the monitor anymore. because there's a bunch of stuff that has to get set up. Now that I have the high RAM, that is the RAM above I/O, I want to use it. And one of the things I want to use it for, or I am using it for now, is config data and buffers for I/O, and other system things. And so to set initial values for that, I have a program in the core ROM that, you know, the values, the starting values are all in the ROM, and those are copied down into RAM. And the point of that is to allow the user, or some program the user is running, to change the behavior of I/O devices, right? So you don't want to be in a situation where you're locked into, this is how the serial port works, and that's it. You're stuck with it. So I'm working on a way to make that, you know, have the system come up with a sane configuration for the peripherals, but then give the user the opportunity to either change out the drivers / handlers for the various I/O functions, or change the config of the thing, like even something as simple as changing the baud rate on a serial port. You know, the idea being, I'd rather not paint the user into a corner that, like, leaving them unable to do some kind of cool thing in the future. So that's the idea. The ROM has all this initialization code. It populates the stuff in RAM. You can change it in RAM at any point. And if you do a cold start, we have cold start and warm start now, which is pretty cool. So basically, there's a value in RAM. When a reset happens, it checks that location for the expected value. If the expected value is not there, then it does a cold start, and the cold start involves copying all that config data down from ROM, and you know, doing some initialization stuff on some of the peripherals, and then right now it passes control to the monitor, but at some point I'm planning to have a menu program in there. When the pageable ROM is in place, it'll check to see if the pageable ROM is there, whether or not there's a cartridge inserted, all this other kind of stuff. If there's storage and a boot program in there, and none of this has been fleshed out yet, but basically doing all this polling to see what's available, and then render this menu to say, you know, run the cartridge, pick a ROM, boot from storage, you know, all that, or run the monitor, all that kind of stuff. And I'm also working on this thing I call the Common I/O handler, which basically is intended to provide a single API to allow kind of standardized communication with the various peripherals that are on the system. So, you know, basically, for example, a 6551 and a 6522, these are two kind of different peripherals, right? And so to make use of these two peripherals without any kind of abstraction layer over them, you basically have to talk two different languages. And my goal with the Common I/O handler was to kind of remove that and say, you want to send a byte out of this port? Here's how you do it, right? You don't have to know what the device is underneath. You just have to know you want to send a byte. And so that's kind of the idea there. There's a couple of things in there about, like, whether you're sending a byte or whether you're sending stuff from a buffer with a terminating character in it, or you're sending a certain number of bytes from a buffer. You know, these are kind of configuration things that, yeah, you do need to know that. But once you've made that determination, you issue the command to the Common I/O handler and what device you want to do this operation on, and it figures out the rest. So anyway, that's kind of what's going on in the Brave New World at this point. The RIBBBIT65 monitor has stagnated at this point. I mean, it's functional. It does what I need it to do. And so I'm planning on doing a rewrite still, but I want to wait until CIOH is completed because I want to use CIOH for the monitor. I don't want the monitor talking directly to the console port for reasons that will become clear later. I already mentioned the cold start, warm start. Again, common I/O handlers, a simplified API to permit configuration of and access to peripherals. Handler routines in ROM referenced by vectors in RAM. So I kind of mentioned this already. The idea being that if the ROM routines are sufficient for you, you don't have to write any additional code. If you want to do something different, you can, and you can do it at the peripheral level. So there's a vector table with a vector for each of the core CIOH functions for each of the 32 base peripherals, right? So 16 system I/O peripherals and 16 user I/O peripherals. And so all those vectors are in a vector table. It's 512 bytes. So that any one of those routines for any one of those peripherals, you can say, I don't like the way it does it with the ROM. I want to write my own. Fine. Of course, that means when you start up the system, you have to update that. But once I get storage on board, it should be possible to overwrite those values on, if you load a config from storage, it should be able to populate those values. So that shouldn't be bad. User assignment of system calls and rerouting of the system console. Haha. So that's why I want to hold off on rewriting the RIBBBIT65 monitor. I want to be able to have the system console, like, at some point in the future, I intend on connecting a keyboard to the RIBBIT65, right? And some kind of a display, whether it's a 40 by 4 LCD character display or an HDMI monitor, something. And so if I do that, I have to be able to split the system console into an input device and an output device, and be able to do that at random, right? So just pick devices. I don't know and care what kind of device it is. This is the stream, right? This is the input stream. This is the output stream. These things have to come to the monitor. So my plan is to create a console device in software, and that will facilitate that. So the RIBBBIT65 monitor will just talk to the console, and it's up to the CIOH and the console device to figure out where the input is coming from and where the output is going to. So this is the memory map as it exists now. So 0 page and CPU stack, that's standard. There's system low RAM, and that runs up to from 200 hex to 5FF hex. And then from 600 to 5FF hex is user RAM. So the idea here is that's the playground for any program that you might be writing or running, or data that's related to programs you're writing or running. The system should not be interfering there. It should be your programs and your data that lives there. 6000 to 60FF hex is the system I/O page. That's 16 ports, each with 16 registers. And then 6100 to 61FF hex is user I/O. And the user I/O, again, it's kind of a greenfield. The only thing that I'm planning to do with system I/O really is putting an interrupt controller at device 0. That's it. Everything else is up to the user. And I don't know. My expectation would be user I/O would be kind of like the Atari 850 interface device, where it's just like, yeah, 9 of them were sold. I don't expect user I/O to get a lot of traction. System high RAM is 6200 to 7 FFF hex, and that is where the bulk of the I/O config, I/O buffers, all that kind of stuff. That's where that takes place. The scratch RAM for various things. Zero page is used. There's some reserved locations in zero page, and I'm probably going to clean up and consolidate some of those going forward. But yeah, zero page is basically only used for vectors at this point and like scratchpad temp values. Then from 8000 to 9 FFF hex, that is paged ROM. So the plan is to have 3 32K ROM chips, 28 256s, each split up into 4 banks, and through a system that I still haven't really settled on yet, you're going to be able to pick one of those 12 8K blocks. There's the 8K block that's on the core ROM chip itself, and another 8K block that would be on a cartridge. So that's kind of the plan there. So that's an 8K window into that page ROM. And then from AOO to FFFF is the core ROM, including the vectors for NMI, reset, and IRQ. So 6200 to 7FFF is now available. We move system resources into the space, peripherals, buffers, config parameters. Already touched on that. Set up vectors in page 0 to access high RAM resources. Yes. I wrote a tool in Python for tracking memory allocation. So there were some eyebrows that were raised. I mentioned this tool on the 6502 CPU family group on Facebook, and there were some people saying, well, why don't you just parse your assembly language for, labels and constants? And I was like, yeah, that really didn't excite me. So I basically wanted to come at it from the other angle. I wanted to be able to say, this is the definition of the memory, and you go ahead and implement it. So basically, this Python program produces an HTML page that looks like this. It's kind of like mapping the Atari. I don't know who remembers that book, but Compute Books back in the, I don't know, I guess it was like 1980, something like that. They came out with a book called Mapping the Atari, and it had the original name for the memory location, like in the assembly code for the operating system, the OS ROM, or the basic ROM. So it had the label, it had the address in decimal and in hex, it had a name for it, and then it had a description and what some of the values would be, and what different, like for instance, if the low nibble meant this and the high nibble meant this, and if you set bit 3 it does such and such, that kind of stuff was in the description. And so basically that's what I did here. And so I got to the point where I wanted to hook something else to another serial port, right, other than the console, and I wanted to be able to do something with it. So one of the things I thought would be cool would be to be able to to print, right, like to do a page dump from memory to a hard copy, so that, let's say I was futzing around and there was a version of a program that was in RAM, right? Because I'm kind of at the point now where I can boot the system up. I can write an assembly language program in Genie. I can assemble it, do a hex dump on it, and do a little bit of magic to create commands for the monitor to just load these bytes into memory, so that I don't have to burn it to the Eeprom and mess around with things that way. But the point is, if I have to change something in the program, like some direct value that's being LDA'd, well, I can do that on the monitor. I can just do a deposit at the appropriate address, and that's fine. But if I want to preserve that, I don't really have a way to do that other than printing. So I bought the little receipt printer that you see there. It's a 40-column dot matrix printer, serial. It runs at 4800 baud. And there's one peculiarity to it, which is it doesn't do RTS CTS. It's what is the signal? I don't remember what the signal is, but it uses one of the other signals on the RS-232 port. So I use that breakout box to just jumper that wire over to RTS, and it works fine. So it's really great, because I wrote a little to validate the CIOH routines for the 6551. I wrote a program to do a hex page dump to the printer, and naturally, in the interest of needless recursion, I had the program dump itself. So that's what you see there. So what is the future? What are the next steps? Well, I want to flesh out the CIOH. Right now, CIOH is very rudimentary. There's some logic that I have to do to handle various things. Like, for instance, there's variations on the base commands for, like, read until terminate character. There's a location in memory where the terminate character is supposed to go. And to save you a step in tedium, and looking up ASCII character values and nonsense like that, there's a couple of options that say continue until null, continue until, new line, that kind of thing. Well, that means I have to take a step and populate that value in memory before running the basic routine. As I said before, I want to develop a software console device to abstract away the concerns about the behavior of the I/O device or devices that your programs are interacting with. And basically, from the standpoint of the console, it's going to be, if there's a byte that's coming in, then it's available for your program. If there's a byte to go out, you send it out. You put it in this location, and the console device takes care of the rest. And then I want to resume development of the interrupt controller. One of the things that I don't have right now is I don't have interrupt-based I/O at all. The RIBBIT65 monitor does a poll of the status byte in the 6551 to see whether a byte has come in, and that's it. So in order to kind of let the machine relax a little bit, I want to get into interrupt-based I/O, and to really do that, I need the interrupt controller, because there's 7, not counting the interrupt controller itself, there's 7 peripherals on the system I/O board that can generate interrupts. Right now, they're dead ending at the interrupt controller socket. Now, as it is at this moment, I could put a jumper wire from, let's say, the console 6551 and run that to the IRQ line, the IRQ outline from the interrupt controller, and the CPU would just see the interrupt and do whatever it's going to do with that. But ultimately, I want to be in a position where one of those 7 devices says, hey, I need to do an interrupt, and that interrupt then goes to the interrupt controller. The interrupt controller recognizes which line has blipped, and it stores that knowledge and then bugs the CPU. The CPU then calls the interrupt controller to find out which device it should see about a man, right? See a man about a horse, whatever. I don't know. The CPU bothers the interrupt controller, pulls it to get the target peripheral, and then the interrupt handler in the ROM will then go have a conversation with that device that is appropriate to that device type. That's the goal. And here's some stuff. If you want to be in touch or follow this project, I'm on Facebook at Ribbit Nerding. That's 3 B's and a 3 for the E. And that's the YouTube channel that this video is released on. And I'm also posting on the Facebook group 6502 CPU. The actual human readable name of it is 6502 CPU Family. If you're into 6502 stuff, there's some great people on that page, in that group, and they're very commonly ready to help you out, answer questions, give you advice, whatever. A lot of great people there. Hello. So here we are. Presentation, info dump. I hope that was interesting, informational, useful. So the next thing I want to do is a demo. There's a few things that I want to do to kind of walk you through what the RIBBBIT65 does, can do, whatever. Okay, that's good. And so basically, this is it. There are 3 programs that I have in pageable ROM, on the main ROM, the core ROM, that I want to run through. First is the serial print test at address 8100, and what that does is it prints a test page out one of the serial ports. And you don't see it in this picture, but there's a Citizen CBM 910 right there, and we'll show that off a little later. Again, this just prints out a test page. This does a page dump. So you tell it, you put whatever page MSB you want to do a page dump on into address 55, and then you run 8460, and it will dump that out to the printer. So that's different from the P command in the RIBBBIT65 monitor, and that's okay. That's something that I can live with. Well, part of the problem is the CBM 910 is a 40-column printer, and so you basically have a choice to make with the CBM 910 printer, in that it's 40 columns. So you can either do 8 bytes across and use up a bunch more paper, or not do that thing and do 16 bytes across like you would with a normal page dump. But it's a little harder to read, and for now, I'm going with the 16 bytes across, just because I'm a masochist, I guess. And then the 8460 here, 8040 does a time passes. So it's just a thing where it writes something to the character display, and then it waits some defined period of time, and then it returns control back to the monitor. And that is the gist of what I'm hoping to achieve with this demo today. So, why don't we get started? Power. Okay, for a brief second there, it said system okay, and then it overwrote that with RIBBIT65 monitor. What that's about is I was thinking along the lines that it might be handy to show a system message up here and then a program message down below. And so on boot up, like before it goes to a menu or any other program, I wanted it to be able to do some basic system diagnostics and report everything's okay. So that was the system okay. Right now the diagnostic tests are not there, but yeah. Anyway, that's completion of boot up, and then cold or warm start. And then it kicks off the first program, which is RIBBIT65 monitor, and that's what that's showing you there. So, let's see. Can I do this again and show all the things we want to show? Yeah, maybe. Okay. So, I guess I'll do the printer stuff first, since that's potentially more exciting. And maybe not. I don't know. It could be not so exciting. I wonder if, since we're going to be doing printer stuff, maybe the display actually doesn't matter. We're going to print things because printing things is exciting. Or so I've been told. All right, so we have focus here, and let me grab my little paper. All right, so let's do a serial printer test. So we'll say R8100, enter. So what we have here is line and column registration, right? So 01, 02, blah, 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 06. It indicates this is printing from the RIBBIT65 to the Citizen CBM 900 via SIO5, which is RS-232-2. There's a dead beef there, and the dead beef is just for picking it out in a page dump or a hex dump, and the column registration is under the dead beef. So you see the first line is 0000, then 11111, then 22222, and then the line under that is repeating counts of 1 to 0. So that's showing you that it's 40 columns and 16 lines, and then the end. So that's that. We're back online, which is great. So let's take a look at page 8400, right? So the first thing I need to do is I need to deposit in 55 the value 84, and then I run 8460. And so what this is a dump of the page 8400, which is in the pageable ROM, and it's showing the actual program that we just ran, starting here at 8460. So isn't that exciting? By gum. So that is, that little doodad actually uses CIOH to send the job out to the printer, or to send the bytes out to the printer. And then in another demonstration of CIOH, we're going to come up and go over here to our delightful little character display, and I am going to run. I didn't want to do that. This mouse is angering me. So I'm going to run 8040 and hit enter, and it changes the display to time passes, and it sits here. I think it's 15 seconds or 20 seconds, and then it flips back over to our 65 monitor. So at some point, I'm going to do a thing with interrupts. Right now, this is just doing incrementing operations internally in the CPU, or writing it out to RAM, but it's all like CPU and memory based. It's not timer interrupt timer out on one of the VIAs or something like that. So at some point I plan to do something along those lines, but right now just demonstrating that the thing can sit there for a little while and change the display and all that kind of stuff, that was kind of the goal with that. So that's demonstrating that CIOH works both for serial 6551 and parallel, or the VIA, right, is 6522. So I'm pretty happy about that. We did the demo now of the CIOH and the Brave New World, and we can access high RAM and all that kind of stuff. And that's pretty cool. But in addition to that, I wanted to do a quick demo of the Eeprom address decoding. Now, I ran into an issue. I believe the Raspberry 400 that I use to show stuff on the stream, I think the USB, one or more of the USB ports is shot. So I struggled with that for about an hour and beat my head against the wall. But now, not that you have any reason to care about the difficulties I'm having with this, but whatever. Anyway, plugged it into another USB port on another machine, and huzzah, it's working. So here's what I'm going to do. I am going to do that. So what are we looking at here? This is my first build of the RIBBIT65 Core Plus board. It's got all the jumpers and stuff and the switches and things. This here, right there, that is a Genio Rev 1.2, and that has instead of a VIA, a 65C22, it has pin sockets into which this board plugs. This is the 6551 daughter board to the Genio, to TTL serial, to a FTDI chip, FTDI or equivalent. This is a breadboard that has an Eeprom here. This is a standard 28 256, the same that I'm using for all the other stuff on this project, and that's programmed by way of a Python application that I wrote, a Python tool. And basically what that does is you define blocks of memory, and it goes ahead and does magic to produce the chip select not, right? The active low chip selects on the output, on the data pins of the EEPROM, based on the values on the address bus. And the address lines have been bumped, depending on how you look at it, up or down by 1 bit. So the actual system A15 line is going to A14 on the ROM chip, and so on. So that means that the address decode resolution is down to 2 bytes, which for my purposes, that's pretty awesome. Yeah, so that's that. So now if I do P&P, and you can see my terminal window, and if I do P0000, that gets us 0 page, right? P0100, that gets us the stack page. See, P0200. This is all very exciting. You know, but then if we go to P6000, so that's the system IO page, right? And okay, it's reading some stuff. That's very exciting. P6100 should give us all 61s. Yeah. And the reason for that is not entirely clear to me, but basically what it's telling us is that there's no reads actually happening there. But then if we go P6200, oh, look at that. P6200 is the beginning of the system high RAM, where all the common IO config and buffers and all that kind of stuff lives. And that goes on, you know, P6300. Let's see what's there. Yeah. So that's all very exciting. Now, if I go P6FOO, you see that there's dead beefs, and then there's a 2A at 6FFF. That's the magic value for a warm start. So on reset, the system looks at that that location. If it sees 2A, it does a warm start. If not, it does a cold start. And I can show you the difference from the standpoint of how long a restart takes by looking at, so the reset vector, which we can determine by doing a P FFOO, right? And if you look at the next to last vector, right? So 00C1, that's C100. That's where the reset program starts, right? So if I do a run C100 and we had that 2A value in 6FFF, right? That's quick. But if I change 6FFF to 42, for example, and then I run C100, it takes a little bit of time, because what it's doing is it's copying, I don't know, like 6 pages out of ROM down into RAM, reinitializing all the IO. So, of course, you don't see any of that on the RIBBBIT65 because the blinking lights don't work and all that kind of stuff. But this is basically telling us that the high RAM, system high RAM is accessible. We can write to it. We can read from it. You know, we can see the ROM, right? So if I do a P8000, this is going to show us the beginning of pageable ROM, which is also terribly exciting. And that's pretty much it. So yeah, that's the EEPROM as address decoding. It's very exciting. So thanks for watching. If you enjoyed this, I'd appreciate a thumbs up. If you like my content, please subscribe. Please check out the 6502 CPU family group on Facebook if you're on Facebook and you're into 6502 stuff. Ribbit Nerding is also has a page on Facebook. It's Ribbit with 3 B's, Nerding with a 3 for an E, all one word. And yeah, that's very cool. So thanks for watching, and we'll see you next time.